Hello again. This is DI504, Foundations of Deep Learning, and this week we are going to be covering a title which is quite crucial for the start of the age of deep learning, I should say, maybe, because maybe we should close the door. Can anybody help me to close the door, guys? Thank you very much. Sorry about that. Sorry, guys. So the first 2 weeks was like an introduction to the subject, because most of you haven't taken any introductory level course on machine learning and this field, maybe I should say, the field of artificial intelligence. So the first 2 weeks was intended to give you an idea about the fundamental concepts. And the previous week, we have talked about neural networks, why neural networks are called as computational graphs, and how can we train them, how can we find the weights of a neural network. And we have learned, having learned the fundamental concepts such as score function, loss function, optimization, weights, parameter optimization, and etc., we were kind of ready for most of the concepts that we need to learn in this course. And we are starting convolutional neural networks this week. I'm going to be talking about convolutional neural networks, but the important thing is, after you learn what, thank you. After you learn what convolutional neural networks are, you will have an understanding of deep learning architecture completely for the first time in this course. Good, let us begin. So the same summary that I was trying to make a couple of minutes ago. We have learned those loss functions and artificial neural networks. Now we will talk about a specific type of artificial neural networks, which is called the convolutional neural networks. Okay, so you may have heard things about convolution. If you're coming from engineering background, especially electrical engineering guys, you know what convolution is. Or if you're coming from mathematics or statistics, you also know what convolution is, or any other engineering field. Convolution is a mathematical operator. It's like a function operator. And basically, convolution, which is very similar to correlation in nature, is kind of used in the engineering or statistics world, or if you're coming from the field of image processing, as an operator to extract some meaning from a signal, or to calculate the resemblance of two signals, and the resemblance between two signals. That was the idea. So how can we use this in neural networks? Actually, how we use this in neural networks is related to the early ages of image processing. So from now on, actually, you might guess that the type of deep learning architectures that include convolutional neural networks are actually related to computer vision, sound processing, and that kind of signal processing based stuff. From now on, you're going to understand that there are different types of deep learning architectures and different types of deep learning models which are suitable for different types of deep learning problems, hence different types of deep learning data types. So for an image, you use some sort of architecture. For sound, you use some sort of architecture. For text, language, you use another type of architecture. Because in the end, remember from the previous weeks, what we are trying to do as a first step is, in deep learning, to extract abstract features from huge data. We have large-scale data. In its raw form, it is difficult to understand and analyze that data for you and for the machine learning algorithm. So the first thing that a deep learning algorithm does is it extracts high-level features from it. And if it is actually signals like sound or image, we are going to use these kind of networks, which are convolutional networks, because actually convolution operation was a very fundamental operation of the early ages of image processing. If you have ever taken a course on image processing, you don't have to in this course. You know that you convolve images or sound, the same, with so-called filters, or they are also called kernels, to extract some low-level features. For example, this is an image. Actually, this is it's not a grayscale image, so it is not, I mean, theoretically, this figure is not theoretically true, but it's meant to give you an idea about it. When you convolve this kernel over this image, convolving means applying this operator. What does it mathematically mean? I'm going to get it to it in the next slides. You obtain something like this. So what is this? I mean, if you can see it, it is difficult to see it in the classroom because of the projector, but Zoom guys can see it clearly. It is like the edges, hard edges of the image. So this was like a kernel. Actually, this is called the Laplacian one, Laplacian kernel. It was like extracting the edges of the image. And in the image processing world, these kernels were very, very, I mean, widely used. They are famous. Sobel operator, canny edge detector, Laplacian of Gaussian. There are a lot of filters, kernels, these discrete operators that you convolve with images to obtain some sort of low-level information from the image. I call this low-level information because edges in an image is a very low-level feature you can get from the image. But it is a sort of information that you can get from an image. I mean, by just checking at the edges of an image, there could be problems that you can solve. I mean, before the age of deep learning, image processing systems were implemented in the industry. For example, you have a conveyor belt, you have some processing and products, you want to just detect some products, wrong products, for example. You write an image processing algorithm with a camera over the conveyor belt, and they did these kind of things actually. So convolution was able to extract low-level features mathematically. Actually, in 2012, researchers of deep learning, this Alex Krizhevsky, the famous guy who have found AlexNet, which we are going to cover today, found a way to properly train networks that use convolution. However, don't get me wrong, the usage of convolution in neural networks dates back earlier. Actually, the first idea was proposed by some guy called Yann LeCun. He is the AI research head of Facebook today. He's a very famous guy. And he was a student of Jeffrey Hinton, who is the guy also who was the supervisor of Alex Krizhevsky in AlexNet. So these guys, Hinton's group, have been working on this idea of applying convolution to neural networks for like 20, 25 years. In the end, in AlexNet in 2012, they were successful to train it. Why they were successful in AlexNet, what are the details of AlexNet, we are going to cover today. Okay, so what is exactly convolution in an image? Well, this operator can be very briefly explained as this guy. So this is the image, imagine. That image is a grayscale image because that image, their example was a color image. So a color image has multiple channels. If you are into image processing, you know that a color image has 3 channels. So it has a resolution of 100 by 100, which means you have 100 by 100 times 3 number of pixel values in a color image. Imagine I'm working on a grayscale image, which is a single channel, which means if the resolution of the image is m by n, like this being m and this being n, I have only m by n, m times n number of pixel values, okay? When I apply a kernel, a convolutional filter over the image, what I do is, this is the image, this is actually an edge operator, which will detect the vertical edges. What I do is, I just element-wise multiply each element here, -1 times 3, 0 times 0. It is like I'm taking the center of the part of the image as here, and it is the center. And I'm doing this operation, guys. Element-wise multiplication, and then summing up. Actually, if you scan this filter all over the image, changing this center, this one, then this one, then this one, then this one, then this one, all over the image, you will have values for the output image, right? Not for the edge values. We are going to get there. Actually, this is what convolution operation is. It is no different than this operation. If you clearly examine the mathematics of this operation, it is this, nothing else. Okay? Of course, since this is a 2-dimensional image, this formula becomes a double sigma notation. But it doesn't matter. I mean, you're just scanning the image. You're doing a raster scan over the image on the kernel. So this is actually convolving on an image. However, be careful, in convolution, actually we reverse the filter. Actually, this filter is G of n, and we are taking the reverse of the filter. And actually, if in signal processing, some filters are complex, have complex values, we are taking the complex conjugate of the filter. But in image processing, this is usually not mentioned, because in image processing, the pixel values and the kernel values are real values. So it is like we forget that there was a complex conjugate operation in convolution. We don't care, okay? So it is like convolution, I should have said. And actually, this operation, if you don't reverse it, and if you assume that the values are real, is actually the correlation operation itself. So correlation operation is you don't reverse the filter and you don't get the complex conjugate of the filter. So if you have a filter which is symmetrical and which is real, in that case, and if the signal is real as well, in that case, convolution and correlation operation becomes the same. And in most of the image processing problems, and this applies for convolutional neural networks as well, the operation we do is called convolution. However, it is actually correlation. That's something funny about convolutional neural networks. Actually, they are kind of correlation neural networks, whatever. So we do this simple operation when we are doing some sort of image processing. The idea of convolutional neural networks is actually applying very, very large number of these filters over an image and making the network learn the filters itself. Remember, what I said was in deep learning, you make the model learn how to extract the features. And this guy is used to extract the features. So somehow in our convolutional neural network, there should be a mechanism so that these kernel values are learned. What kind of features I need, I'm going to learn them. We're going to get there. Okay, so before continuing to the actual convolutional neural networks, there's a, magnificent background of convolutional neural networks related to the biology of the mammals, I should have said, because it's mammals mainly. It is what, and previously in the previous century, like in the 60s, researchers have realized that we as humans, I mean, they've done tests in cats as well, because our brain structure is frankly not so different when it comes to perception. We are doing some sort of convolution operation. They've done tests.
Can I ask a question?
Please.
For the previous page?
Yes.
How can we determine the size of the convolutional filter?
Yes, for convolution, your friend is asking, how will I decide the size of the convolution filter? Are you asking for convolutional neural networks, or are you asking for image processing?
Convolutional networks.
Convolutional networks, I'm going to be coming to that kind of decisions in a couple of slides. So let me not answer it yet. But if you're asking regarding image processing, although it is beyond the scope of this course, I can answer. And the answer would be, that's an handcrafted design. It will depend on the type of problem you're going to solve. Okay?
Okay.
Okay, we are going to get there. So don't worry, we are going to be delving very deep into convolutional neural networks.
Okay.
So these kind of questions will all be answered.
Okay,
so what they realized was the mammal brain has some specific parts which can detect edges, corners, and etc. And that led researchers to believe that we have some sort of signal processing, just like the convolutional filters in image processing, that could help us detect hard edges, hard corners in an image. They've done tests with cats to stimulate these kind of hard edges and blobs. And they realized that we actually have those. They've put electrical signals, just signal detectors in the brain, and they've shown different types of hard figures with hard edges and blobs. These are called blobs. These are called oriented hard edges. And they've checked the responses, and they realized that when you have these hard edges and blobs, which are actually in image processing, the very low level features, some special part of the brain was stimulated. Today we know that it is the visual cortex. It's towards the back of our brain. It is where the first level image processing is done in our brain. So it is like we have a part of our brain which we get the image into, and we apply some sort of filters, and we detect edges and blobs and etc. And this part is so complicated that this extraction is in a way hierarchical. We first extract edges, blobs, then combining this information of edges, blobs, we construct higher features, and combine them again, we construct higher features until we get abstract features like face or, I don't know, feel, whatever. They've speculated on this. So this was actually the first inspiration that led computer scientists to work on models like this, okay? And they have come up with these two types of cells here. I'm not going to get into the details. Some simple cells that are capable of getting some bars or blobs, and more complex cells which are capable of, in another part of the brain, which are capable of extracting higher level features obtained from the other ones. So this led the researchers to believe that we have different hierarchical levels of our brain, which we can extract low level features first, then create higher level features using the low level features, etc., etc. Actually, that's the idea of the convolutional neural networks. And this is the visual cortex in our human brain. It's somewhere here, guys, okay? And it's connected to your eyes. The nerves coming from the eyes, and it's very complicated. We don't know the details of it, but that's the best we can get near to convolutional neural networks. So convolutional neural networks was inspired by this idea. What they said was, okay, we have some simple convolution-like filters in our brain. What we can do is, let's create layered architectures, which first create some features. Then in the next layer, those features, the results of those features, let's call them activations, are used to create relatively higher level features. And with this hierarchical approach, maybe we can create abstract and much higher level features, just like our brain does, because these guys were the guys who were working on handcrafted features by then as well. So maybe that's a good idea, they said. And actually this was first in 87 by LeCun, when he was a postdoc student back then. And they worked on this. And this led us to the idea of convolutional neural networks. Now I'm going to get into the very details of the convolutional neural networks. What is the difference compared to the usual artificial neural networks, or multi-layer perceptrons as we know them, fully connected layers, okay? Previously, what we saw was the artificial neural network, in which every node was connected to every node. However, what we're trying to simulate is the convolution operation. And in the convolution operation, you have a filter which is moving, right? So not everything is connected to everything all the time. When you're calculating some part of an edge, whatever, if it's an edge, it depends on the weights of the kernel, you're using a regional calculation. So the connections of a convolutional neural network must be different, right? So that's the idea of convolutional neural networks. So the first one, the previous ANN, was everybody is connected to everybody. This is a layer, this is another layer, everyone is connected to everyone. We're going to call them dense layers because they have dense number of dense connections, or fully connected layers, or linear layers, multi-layer perceptrons, artificial neural networks, whatever. They have so many names. Okay, and they will be called in convolutional neural network architecture literature fully connected layers. Usually, in some libraries they are called linear and dense layers. But when I say fully connected layer, remember the conventional neural network connection. So in convolutional neural networks, just like I said, you have only connections to the required regional part in the signal. So in a convolution, what defines a convolutional layer is that kernel, or if you have more than kernel, the set of kernels, filters, okay? So in this example, I have only one filter. However, I can have more than one. Let's go over the example when we only have one. So this is the image. So in the previous example, this was a grayscale image because why? Because it has a single depth. However, in CFAR10, the data set we used in the previous weeks, remember, the images were 32 by 32 by 3 because they were color images. This was the depth, okay? From now on, I'm going to call these dimensions as spatial dimensions, coming from the word space, because they define how the signal is constructed in space. For an image, the spatial dimensions is 2, this m by n. For a sound, the spatial dimension, is there a spatial dimension? I think for a sound, there's only the temporal dimension because it's if you have never seen a sound signal, it is just level going up and down in the time dimension. However, when you're processing time signals, if you're from MMI, you know this, you can create a frequency domain which may be thought of as a spatial dimension and the subject beyond the scope of this course. So these will be called the spatial dimensions. And I'm going to be calling this the depth. These two dimensions, the separation of these two dimensions, the definition of these two dimensions will be very important for us when we are dealing with convolutional neural networks. Because in the convolutional neural networks, the kernel itself will go over the spatial dimension, which means if my signal is two-dimensional in the spatial domain, like an image, I will have a filter which is two-dimensional. And if my signal has a depth of 3, my kernel must have a depth of 3 as well. Otherwise, I won't be able to raster scan my kernel over it, okay? Since this is a two-dimensional image with single depth in this example, the kernel is also two-dimensional and a single depth, one filter. Not one filter, it's one filter, but one filter's depth is 1. Okay, so how can we do this? In convolutional neural networks, if you have this spatial dimensions of 2, you have a two-dimensional filter. If the depth is n, you have the same depth in the filter. Okay, filter always extends the full depth of the input value. They should be the same. And what I do is I raster scan it over the image. This value, the size of the filter, is usually smaller than the size of the image. It cannot be larger because then you won't be able to just go over it over the image. What happens if they are the same? Can anybody think of that? If this is 32 by 32 by 3, and this is 32 by 32 by 3, I won't be able to go over the image. What would happen then?
We can end up with the same image.
It won't end up with the same image because you're multiplying it. Your friend is proposing that it may end up as the same image. Well, we don't know the values of the filter. The filter values can be very different. So when you multiply them, you end up with something bizarre maybe. Actually, you end up, if you don't do something called padding, what you end up is actually a single pixel because you cannot raster scan over the image. And is there an application for it? There could be, but I was just trying to do a thought experiment. Okay, so when I get back to my regular example in which the filters are usually smaller than the image, what we do is we slide over the image in the spatial dimensions, spatially. The depths are always the same. Okay, very good. So what I do is I slide over the image. For each center that corresponds to that I just put my filter on, I calculate the weights times the pixel values, if they are pixels. And for each filter, I have a constant bias. I add it. And I also have an activation function. Remember the perceptron? Because the perceptron was actually, you multiply with the weights, you sum them up, you add the bias, and apply an activation filter. That's actually a convolutional layer, nothing else. We call it convolutional block with the activation function, please. Your friend is asking, when we slide over the image, do we make overlapping slides or do we just jump over them? Both are possible. This is a parameter for a convolutional neural network. That's called stride. We are going to cover it in the following slides. And there are reasons for using it and not using it. Okay, so bear with me. We are going to get there in a couple of slides. He was asking a question about what we know in convolutional neural networks as stride. How do I make the slide? Do I jump or do I get to overlapping windows 1 pixel at a time? We're going to get there. Okay. So guys, when I apply this filter, as you can see, remember, this is a 5x5 filter. So I won't be able to use this, just fit the center of the filter to the first pixel. Why? Because of the borders. Remember this figure? I could start, this is a 3x3 filter, I could start from this pixel. I could not start from this pixel because if I started from this pixel, matching the first pixel to the center of the filter, then where would this filter value match? I don't have a value there. That's why if I don't pad any values, because that's a possibility I'm going to get in a couple of minutes, what happens is, if I have a 5x5 filter, I will be able to start at the pixel 3x3 in the image. And in the end, when I make that slide over the image, the output map, which I call the activation map, will be smaller. And I will lose a dimension of 2 in all borders, right? That's why if this is 32x32, it's going to make 28x28. And since I am multiplying every depth and summing them up, so it is like I have a triple sum. How I do it like this, guys. What I do is, I do it like this. Sorry. So I have a triple sum. So this is 1 to 32, and from 1 to 32, depth from 1 to 3. So the kernel, let's say this is a small m. So the kernel moves and the image moves. I sum them up. So it's M and D, and I move the kernel. Okay, to move the kernel, I have another loop here. So that's how I do it. Okay. So in the end, for this single filter, I will have an activation map of 28x28x1. However, if I have another filter, if I had another filter, not only one 5x5x3 filter, the output map would be one more. So by increasing the number of filters, I can increase the depth of the activation map. Well, at this point, I directly jump into these calculations. At this point, it may sound a bit, I don't know, meaningless to you, because why are we doing this? How are we going to use them? Bear with me, just understand the architecture. The architecture will make a lot of sense when we come to real convolutional neural network CNN architectures, okay? So as you can see, if the input is this value, it has 2 spatial dimensions, 32x32. Then the filter has 2 spatial dimensions as well. If the depth is 3, this should be 3. They are both green, that's why. And if I have 6 filters, then the output depth will be 6 as well. That's the very basic logic of how convolutional neural networks work. So why would I use 6 filters? Maybe one filter was to find the vertical edges. Maybe another filter was to find horizontal edges. Maybe a filter was used somehow in mathematical values to find red blobs. Blob is like something there, just like a Gaussian figure. Or one was to find blue blobs. One was to find, I don't know, directionless corners, just Laplacian of Gaussian. Because when you get these low-level information, maybe you can use them to create a higher level feature. That's the idea, that's how you do it. In one layer, you calculate this. In another layer, you calculate that. That's why we have layers of convolutional. We have many convolutional layers in a convolutional neural network. At each convolutional layer, we have a number of filters. So at the first convolutional layer, you have 6 number of 5 by 5 by 3 filters, right? Now I have an activation of 28 by 28 by 6. Now forget it, this is the input to the next convolutional layer. Since the depth is 6, I should have filters of, for example, m by n times 6 here, because the depth of this input to this layer, the output of this layer is the input to this layer, should be the same. So this 6 and 6 should be the same, the 3 and 3 should be the same. But I have 10 number of filters. Then the activation here would be 24 by 24 by 10. I'm using 5 by 5 again. I'm losing the edges, the borders. So that's how convolutional layers work. And the idea of convolutional layers is you have different low-level features and you have the output of different convolutional features. So the activations you obtain here is the strength of horizontal edges, the strength of vertical edges, and etc. Those kind of simple features. At this layer, this convolutional layer convolves that information together to extract a higher representation. So a serial, linear, hierarchical feature extraction mechanism, which is inspired from our mammal brain. Okay, so how come it works and how come we have the correct convolutional weight values that it works? Well, that's the beauty of it. We are going to get there. So as you can see, because of the borders, I'm losing spatial dimensions. But there's a cure for that. I'm going to get there. So in order to fit the filter to the edge points, some actuations cannot be calculated. Why? Because I have, for example, the input is 7 by 7 and the filter is 3 by 3. The output will be 5 by 5 because the only centers that I'm going to be using is these guys. So I'll be using this center, this. So inside this, I'm going to be using these. Why? Because I will be able to fit my first 3 by 3 filter. Sorry. Allah. Okay, I have it. So it is like I'll be able to fit my filter here first, right? I won't, so the center of the filter will start from here. I won't be able to start from here. That was why every activation got smaller and smaller from the borders. And depending on the size of the filter, the effect of this shrink can increase, right? Okay, there is a cure for that, which is called padding. So now about your question, padding is one thing, and about your friend's question, will I jump from here to here or here to here? That jump in convolutional neural networks is called a stride, guys. So if you have stride 1, then you will do this first with this center. Then you are going to do, if the stride is 1, you will move 1 pixel and do this, the next guy. But if stride is 2, for example, you are going to be jumping directly to 2 pixels ahead. So it will be like only the red ones jump this way, jump this guy, this guy. Only these. The values in between, the centers in between will be omitted. And if you have a jump value, stride value of 2, the output will be not 5 by 5, this time 3 by 3, depending on your jump value. Why would I want to do that? Well, they have meaningful explanations when it comes to extracting features. We are going to get there. We first understand the mechanisms that rule the convolutional networks. Okay. So when you apply stride, I jump from here to here. Good, stride to here. So to solve the first one, what we do is something that we get from signal processing again. when you have a signal and when you convolve it to another signal, we know that the signal, the actuation output will be shrinked. To avoid it, what we do is we pad zeros around the signal, depending on the filter type. For example, if you have a 3x3 filter, padding only one layer of zeros to all borders will be enough. But if you have a 5x5 filter, and if you want to get the same value of the same sized output with the input in spatial dimensions, then you would need, if your filter is 5x5, then you will need 2 layers of padding in all borders, for example. So there's a mathematics of it, which I'm going to be giving you the formula in a couple of slides. So in convolutional neural network literature, when we say padding equals the same, because padding is a number. Padding is a 4-dimensional number indicating how many layers of, how many rows and columns of padding you do in 4 dimensions, right? There's one padding here, one padding, one padding, one padding. So it is a number actually. But when we say the same, it means calculate padding for each border by checking the filter. If the filter is 3x3, then pad 1s all over the image. If the filter is 5x5, then pad 2s in all borders of the image. So when I say padding same, that would mean that I want the spatial dimensions of the output to be equal to the spatial dimensions of the input. Okay, good. So there should be a formula for it. There is a formula for it. That's quite simple, guys. So for a 2D convolutional layer, which means the input signal is 2-dimensional in the spatial coordinates. It could be 3-dimensional or 4-dimensional, and we have those. But for the sake of simplicity, I'm going to provide this formula in 2 dimensions, which is just straight, which can be applied to multiple dimensions in a straightforward manner, which is for the output size of a 2D convolutional layer with input spatial dimensions n by n. So your image is n by n. And your filter size is k times L times F, okay? And padding of P. I don't have the depth dimensions here, guys. This is k by L is the spatial dimensions of the filter. So this is 100 by 100, for example. This is 3 by 3. F is the number of filters, okay, not the depth, because I don't need the depth for this formula. I know that the input depth and the filter depth must be the same. I don't care. So the output will be decided according to what padding and stride is. Padding could be different for all borders. Usually they are symmetrical in a dimension. I mean, if you have one padding in the north direction, you have one padding in the south direction. So this is how you get it. And the stride of S, the number of jumps. Again, stride is a value of the same dimensions of the spatial dimension, because you could do one stride, one jump in horizontal direction for an image, but you may choose to do, I mean, more jumps, stride value higher than one for the vertical dimension, maybe. It's mathematically possible. Does it have a meaning? It has for some signals. We are going to get there. You can. So for both dimensions, the rows and columns, this is weight and this is height, okay? This is width and this is height. Well, how you calculate it is m minus k. So if this is a 100 by 100 image, let's go over it by numbers. It's simple. So let's use the same numbers, 32 by 32. Okay, this is 5 by 5, okay? So 32 minus 5. Imagine for the first example, I don't have any padding. This is 2 times p, which is assuming that you have the same type of padding in the both borders of that dimension, okay? Imagine in the first example, it was 0, okay? I put 2 times 0, and stride is 1. As you can see, this value is 28. That's why we had 28 in the first output. Very simple. We have +1. Don't forget that. We have +1. Okay? That's the formulation, nothing else. You use this formulation to calculate the output activation value in a convolutional neural network? Well, will I need this information? Convolutional neural networks, especially the simple ones, are handcrafted designs. I mean, the features that the convolutional neural network extracts are not handcrafted. It automatically learns the features. But how you design the convolutional neural network, how many layers you have, how many activations you will have, what are you trying to do, that's an handcrafted design. So when you are designing a convolutional neural network for a problem, like an image processing or sound processing problem, you design the network. And while you are designing the network, you need to know these parameters and the output values and activation values. There are tools for that. I don't have to tell you this in Python and MATLAB. However, that's the mathematics of it and how it's done. Please. In different dimensions, yes. But in a single dimension, in the conventional convolutional network, no. So imagine, so it was a bit confusing, right? So let me just get to the previous page. So for example, this was a stride of 2, right? What I had was, since I had a stride of 2, I was jumping from here to here. So this is jump of 2, S of 2. Imagine I have a stride vector of 2 and 1, which means in this direction, stride is 2. In this direction, stride is 1. In that case, I'm going to get this. I'm going to get this. I'm going to get this. The next one will have a center of this because the stride is here. I'm going to get this. An unbalanced, unsymmetrical stride. Usually we don't do that for images because in images, the pixels are assumed to be square in both dimensions. However, there are spatial signals where the dimensions are not related just like an image is. For example, the spectrogram obtained from a sound signal. I mean, this didn't make sense for many of you, but for example, in those cases, we use different strides and different padding and different filter sizes, not 3 by 3, 10 by 4 kind of. How we select the filter size is something important. Actually, what we are trying to build up is related to something called the receptive field. I'm going to talk about it. Get the mathematics now. Then we're going to discuss those. Okay, before I finish the first hour, let me just go over. Please. Well, yes, well, not using convolutional layers. That means that requires a different type of layer. Your friend is asking, can we just lower down the resolution of the activations in the network? Yes, there is actually a layer for that. It's called a pooling layer, which I'm going to be covering in a couple of slides. But we don't do it with convolutional networks. And it has a reason as well. I mean, there's a meaning as well. We're going to get there. Okay, so this was padding. This was the formula. So I'm going to be showing you, before I finish this first hour, I'm going to be showing you the first layer of the famous AlexNet. Now, it's the first time you're seeing an actual famous, very well-known convolutional neural network architecture. The input to AlexNet is an RGB image of size 227 by 227. Why this value? Don't think about it. It's related to a database, and actually the database is 224, but in this study it was 227. Whatever, just take it. The first layer, after the input layer, we have a convolutional layer. The convolutional layer has 96 filters. The filter size is 11 by 11 by 3. It must be 3 because this is an RGB image. I have a padding of 0, right? And I have a stride of 4. I'm going to jump. As you can see, it's all symmetrical. M by N equal, the filter size is equal, the stride equal. Let's calculate it using this formula. If you calculate it using that formula, what you obtain is, let me calculate it here very quickly, minus the filter size, remember? Filter size plus 2 times padding over 4 plus 1, if you can just follow the formula. And what does this value calculate? I mean, if you calculate it, it is actually 55. So at the very first layer of AlexNet, we obtain some low-level actuations with a resolution of 55 by 55. And we have 96 of them. How they look like, we're going to get there, don't worry. So this is AlexNet. I mean, so let's go over the, and we have a bias for it. So one thing important, I have 96 11 by 3 filters. So the number of weights I keep in this layer, because each filter has different values, I have these number of weights. If you calculate it, it makes a pretty much number, like 30,000. And for each filter, I have a single bias. Because remember, how you do it was, you have calculated the weights with that part of the image, you sum them up, and you added a bias, and you applied an activation function. Actually, the activation function is ReLU. You remember ReLU? ReLU was a very simple activation function in which negative values are 0. The output for a negative value is 0. The output for a positive value is itself. Okay, so the learnable parameters, we say the learnable parameters or biases, because when training, these are the parameters we will be trying to learn. So the weights of AlexNet is not provided by somebody. It was learned. For this layer only is like 34,000. And in convolutional neural networks, AlexNet has 7 layers, but you may have hundreds of layers. Imagine the number of parameters you learn. It makes hundreds, thousands, millions. That's why, remember our discussion in optimization, we were always giving the feature space of 2 dimensions. For example, the spherical and shape and color dimension. The dimensions you try to optimize in a convolutional neural network is hundreds of thousands because of the number of parameters in the system. That's why they are very difficult to train. And the nice thing about AlexNet was, it was the first study that was able to train it properly. They found a way to train it properly, and they had GPUs, of course, because GPU technology evolved as well. Good. So we know how to calculate a single layer of AlexNet now. Good. Any questions about how we calculate the activation values in a convolutional layer? Okay, now I continue. Now I'm going to talk about, okay, let me just, this is a long discussion. I'm going to leave it to the next hour. So any questions about convolutional layers and activations?
Hocam ben bir şey sorabilir miyim acaba? Strike burada 3'e 3 olsa küsuratlı bir şey çıkacaktı weights. O zaman ne yapıyoruz? Yani küsuratlı olmamasını mı sağlayacak şekilde ayarlıyoruz strike'ı?
Your friend is asking a very good question. Depending on the value of the strike, which is the denominator, the output activations can be non-integers, he's saying. That's exactly true. Let's go. What happens then? What we say, do we choose it as, such that we make it integer, or what happens if we don't make it integer? Well, first of all, what happens if you don't choose the activations to be integers? Choose the strike value properly so that the activations will not be integers. It depends on on how the deep learning library you're using is implemented, how it's going to handle it. Let's forget how the library is implemented. Let's see the real application in the real world. So I'm going to choose a stride of 3 for this example, okay? And we're going to see what happens. You're going to see, I'm going to choose 3. So this will be the first guy, okay? I'm jumping 3. This will be the first guy. What is the next guy? Not this one, not this one. I'm finished. So if I've chosen stride 3 by 3, same in both dimensions, this will be the center. And this will be the next one. So let's draw the where the weights are convolved with. I'm going to convolve it with this. I'm going to convolve with this area. because I'm assuming that padding is 0, okay, in all dimensions, okay. And I'm convolving it with this. I'm convolving it with this. So it is not non-integer. I just didn't use these parts. And that's a bad design for a convolutional neural network because you are not using some part of the signal, and the output will be 2 by 2 is shifted because you have a 7 by 7 output and you have a 2 by 2 output. The center of this output will be here. However, the center of the input was here. You experience a shift and you don't use some of the information of the input. So what you will get is this. It's going to be a bad design because you're shifting your signal, because if you're trying to localize something, you're losing the localization and you're not using the input, some part of the input. So that would be the result of it. Answer to your question? Yes,
Evet hocam, teşekkür ederim.
Okay, and your question from the classroom? So what is it? When you apply the formula, you mean, right? So it's going to make a non-integer value. So what happens is you apply a floor operation. You get the smallest integer value that is you get from the output. So yeah, let's apply it. Your friend is asking what I understand. What happens if you apply the formula? What happens? Sorry. 7 minus 3 plus 2 times 0 over stride was 3 plus 1. Okay, this it's okay. Over 3 plus 1 floor is equal to 2. That's the problem. There's always the plus 1. Okay, and we'll continue in the next hour.